Hello, everybody. We're going to get started with the next session. It's a session on reinforcement learning to follow appropriately on Peter's talk. And the first talk will be on ELF, an extensive, lightweight, and flexible framework for game research, or for real-time strategy games. And this will be presented by Yuandong Chen.
Thanks for introduction. So good afternoon, everyone. My name is Yuandong Tian from Facebook AI Research. Today, I'm going to talk about ELF, an extensive, lightweight, and flexible framework for game research. This is a joint work with Chucheng Gong, Wenli Shang, Yuxin Wu, and Larry Zinnick. So imagine that you are a beginner of reinforcement learning and you want to explore that space a little bit. You are very excited about the power and feel that, oh, maybe I can train my own AlphaGo Zero. And then you pick up your favorite textbook and learn that in reinforcement learning, the agent repeatedly takes actions, given the current states, receive rewards, goes to the next state, and so on. You think this is very easy. You think this is basically a for loop and should be very easy, and you can write some Python code to see what's going on. But actually design a practical reinforcement system is way beyond a simple for loop. There are like a few design choices that has to be made correctly in order to make the entire system working well. So the first choice that people need to think about is choices between different kinds of computation architectures. For example, whether we should use CPUs or GPUs or maybe like alternative architectures. Maybe we should think about like different methods such as we can use like on-policy approach or a policy approach. On-policy approach creates data by on-the-fly simulations, but might need like a lot of computational powers. And on the other side, all-policy approaches uses replays and human demonstrations that help sample efficiency, but might be irrelevant to the current policy to be optimized. So we really need to find a way to switch between these two different or several different approaches and in a very flexible manner. And thirdly, we also need to choose among different concurrency methods, right? For example, whether we should use multi-threading or multi-processing, and etc., to accelerate training. So in our world, it's actually very hard and non-trivial to design a reinforcement system that is flexible, at the same time is very efficient. So in this talk, we basically propose ELF, an extensive, lightweight, and flexible framework that makes a practical reinforcement system easy and manageable. So for this, ELF puts all the implementations and detailed design into the C++ side and leaving the Python side a simple and easy for loop. And this is as advertised in the text that we have all been reading. So moreover, each time the Python side returns a batch for a neural network model to operate on to improve the efficiency. So there are three important characteristics in ELF. First, it's extensive. Any games with a C++ interface can be incorporated into this environment. And second, it's very lightweight. For example, we have built a simple RTS real-time strategy games engine on top of that. And this engine can run with like 40K frames per second per core on a laptop. So training such an agent on this game will use very minimal resources. Literally like a single GPU with multiple CPUs, and it will only take half a day. So this actually made people happy about exploring new ideas and new thoughts on real-time strategy games. From which, if you want to run StarCraft 1, things will become much more complicated. And finally, it's flexible. Thanks to its design, it's very easy to change the topology between environment and actors, between environments and optimizers, without a big shift from the environment side, from the framework side itself. The game environment can also be parameterized, and we also offer different choices of reinforcement learning algorithms. So in terms of extensibility, ELF supports different types of games. This includes board games such as Go and arcade learning environment. ELF also includes our homemade RTS engines, which includes three environments such as mini RTS, capture the flag, and tower defense. In the future, we will include more games. So the ELF platform is lightweight and can be used with the computational efficient manner. So we have compared ELF with OpenAI Gene in terms of POM. So when OpenAI Gene performance deteriorates when we are going to use more cores, and because of this inter-process communication, the overall efficiency goes down. But however, our framework makes full use of parallelization with strong performance on more cores. And in terms of flexibility, let's start with some scenarios. So first of all, if we want to just use ELF for evaluation, we can just use a simple for loop on the Python side. And on the C side, the agent basically receives the current state, sends them to Python for network evaluation, and gets the action back and continue. So it's very simple. But what happens if we want to add some training? We want to, for example, we want to train the agent so that it becomes better and better. So that's actually easy in ELF. In that case, we just collect the data from the most recent agent trajectories and add a branch in the while loop to deal with the trajectories to update the model parameters. And at the same time, the active branch is still driving the agent forward. So what if we want to do self-play, which is also very easy? Each time, we can just add a new agent in the environment and have two branches dealing with the two agents independently. So ELF has a built-in mechanism to automatically group the relevant states together and send them to the right agent and the right network. So if you want to train a model for one agent, we can just add another branch in the while loop, as seen in the previous slides. We can do definitely similar things for multi-agent. And we can also do Monte Carlo tree search with the same framework. Right? The search is basically performed on the C side, and whenever the search wants the network to evaluate the current situation, it will send the states to ELF, and ELF will automatically group states together from different game instances for battery efficiency. So how ELF is designed? So first, we put all the game instances into what is called a producer in the C side. Each game will have a history buffer that actually holds the recent history. So we have multiple instances in this C side, and they are all parallelized in multi-threaded setting. So, and besides all the game threads, there is a collector in a separate thread that collects the states of multiple games. So once enough number of states are collected, then the collector will send the batch states to the Python side. Then the distributor in the Python side will distribute the batch to the desired models. This model could be either an actor, which will give reply to the C side and also drive the agent forward. It can also send to an optimizer that will update the model parameters but doesn't emit a return. And finally, the entire framework is embedded into a single process, which makes it very lightweight, and there's no much overhead. So our platform is much simpler and lightweight compared to the previous platform that might require distributed training. This includes Gloria, linear actor-critic methods, and also recently GA3C or batch A3C approaches. And not only that, we can also offer tremendous flexibility and can simulate these previous settings easily. So this not only include off-policy training, actor-critic, and batch A3C, you can also include other interesting cases as well, such as self-play and Monte Carlo tree search, that are potentially very helpful in training recent strong AI agents such as AlphaGo 0 or maybe AlphaZero. So as a proof of concept, we show that the usability of our framework in a miniature real-time strategy game called the Mini-RTS. So Mini-RTS is a small game that captures basic dynamics of real-time strategy games. This includes gather resources, build workers, build units, explore unknown territories, defend the opponent's attack, and take down the enemy. Note that the game is incomplete formation, so which basically means that each player can only see the part of the map within the size of its own units. Compared to other platforms, Mini-RTS can run like 40K frames per second per core on a laptop, while running on a cluster it could be faster. So such a speed boost makes it very usable for reinforcement learning research. So Mini-RTS has multiple units. These include bases, resource, barracks, worker, and 2 hyper tanks. For detailed descriptions, please check our paper. To train our bot, we use classic character-critic models and a simple convolutional network whose input is a multi-layered features from the internal data of the game. This includes X and Y location of the units, unit affiliations, hit points, and the player's resources. Note that in our training, the foreground wall is respected so that each player can only see the situations within the sites of all its units. We don't use any reward shaping here. The reward is only available once the game is over, and it's always a +1 or -1. A typical game lasts for 4,000 to 5,000 ticks, and our bots will act every 550 ticks. So as a starting point, instead of specifying action per unit, we use 9 discrete strategic actions as the output action of our model and leave all the details to the rule-based subsystems. For example, when we want to build a barracks, the agent does not need to specify its location, but instead, the lower-level rule-based system will specify it. We train our bot against 2 rule-based AIs. The first is called AI Simple, which will simply build 5 tanks and attack the opponent's base. The second is called Hit and Run, which will build 2 red tanks and try to harass the opponents from time to time. Note that, to be fair, both the rule-based AIs use the same 9 strategic actions as the trained AI. So using our framework, we can train a strong agent with a simple GPU and like 6 CPU in half a day. And here's a video showing that a replay between the trained AI and the simple AI. So you'll see that the trained AI actually learns that when to build barracks and when to build like more troops so that you can defend the enemy, and finally try to use some tactics to take down the opponent. So here So here it builds. The opponent's taking is attacking, but the AI actually take the defense, and after that, the AI actually find a way to use some kind of tactics to attack the opponent's base until it win the game. So using this framework, we have done extensive ablation analysis. By changing the network architecture, we found that using liquid value plus optimization works the best compared to other architectures in terms of win rates against 2 AIs. So here that all these win rates are computed on average over 10K games. So this is basically one of the benefits of our platform. You can evaluate these 10 games in maybe like 2 minutes, so which is extremely fast compared to other frameworks. So here we are training the model with curriculum training, in which we use a mixture AI whose first K decisions are made from the simple AI, while K is decaying when more games have been played. So during the evaluation, all games are played by the trained AI alone. So you will see that after this curriculum setting, the final performance is stronger. We also perform experiment on transfer learning. So if an AI is trained against the AI simple or AI hit and run alone, it will only perform poorly against the other one. But if you train both with a 50-by-50 mixture, then it is generalized quite well on both of the situations. And finally, we also compare our trained bots with medical tree search. Note that medical tree search can access the complete states of the game and knows the perfect dynamics. But our trained bots does not have all this information. But we can still see that our trained AI can achieve comparable performance against medical tree search with model-free reinforcement only. So here are a few ongoing work. So we are going to continue our efforts to make ELF better by incorporating more games, expanding the existing mini-RTS engine so that it becomes more like a formal strategy game. On the research side, we are exploring how to deal with more realistic action space, for example, 1 action per unit, and study how to utilize model-based reinforcement learning and self-play to further boost the performance of our trained AI. And finally, we have open sourced the project, and welcome to use and contribute. If you have any other questions, welcome to our poster session tonight. Thanks for your attention.
Great. Please come to the microphone if you have a question. Let's see where the microphones are. Yes?
So have you tried self-training against itself?
Yeah, we have already tried that. It actually can improve performance further. Yeah, but we haven't reported the number yet.
Have you looked at how the learning scaled beyond the relatively small number of actors that you showed here to, say, the hundreds or larger numbers?
You mean like how many? So you mean like you have like lots of independent actors on the environment? Yeah. So we haven't done that yet, but we will do that in the future. So and we also are working on a distributed version of it, in which you could have multiple actors over different machines.
All right, let's thank the speaker again. Hello, hello, hello. Is that on? All right. The next talk will be on Imagination-Augmented agents for DeepRL. And the talk will be given by Theo Weber. The co-authors are Sebastian Rancanier, Theo Weber, and David Reichert.
Thank you, and good afternoon, everyone. So I'm going to present Imagination-Augmented agents for DeepRL. So in the last years, we've seen many advances in deep reinforcement learning, thanks to the combination of model-free methods in RL and deep neural networks. However, these methods, this approach still has some drawbacks. As mentioned by Peter earlier, these methods tend to be still data inefficient due to the trial and error nature of the training. The second is that these methods typically have limited generalization. So they tend to do well on the kind of environments they were trained on, but say you have the same environment but different task, they don't generalize. Or if you have a new environment composed of elements that you're familiar with, it tends not to generalize. So a possible solution has been proposed, and it's a model-based reinforcement learning, in which we want to build an agent that has an internal model of the world. And effectively, it's able to understand its environment, it's able to understand what would be the consequence of its action in the world. And this would lead to improved performance thanks to the effective combination of unsupervised learning methods for the environment modeling and reinforcement learning. It would also potentially lead to a better performance period because it enables planning. In effect, the agent can assess the effect of its action before actually taking them. Lastly, it could potentially lead to generalization to novel situation because environment model tends to be compositional. In practice, however, model-based RL has been hard to scale up. It's hard to apply to a high-dimensional environment. One of the reasons is that training environment model and using them is both costly and inaccurate. It's costly because environments are very complex and predicting absolutely everything is very difficult. The other issue is that a lot of model-based RL methods tend to trust their models entirely, and they prescribe how you turn a model of the environment into a policy. And so if your model makes a mistake, what can happen is that you have a catastrophic failure of the actions that you take in the real environment. So on the right here, you see a little diagram of a model-free RL agent that takes an observation and computes some form of agent state, and from the agent state computes an action. Here you have a sketch of a model-based RL method that has an environment model, and the environment model is turned into a policy or actions by a planner, which is typically not learned. So in this work, we introduced Imagination-Augmented agents, which is a family of models that combined model-based and model-free aspect in reinforcement learning. So in this approach, what we're going to do is that we're going to have the agent train an environment model, but it's going to use it as a sort of oracle, potentially flawed oracle. And it's going to ask questions, it's going to query the environment model for information, and it's going to receive some predictions which could be helpful or inaccurate, or unhelpful, and it's going to learn to interpret these predictions in order to act. Okay, so I'm going to start by some notation. So an environment model at a high level will be any recurrent model which makes prediction related to the environment at every time step. And these predictions can be kind of anything you want. So I don't restrict what you want to do here. It could be GANs, it could be probabilistic models, it could be value functions. For this work, we have sequence models which predict both the observation, the sensory observation, and the reward. And we are going to assume that the environment model takes as input the current state of the model and an action and predicts the next state of the environment. Okay? So we need a way to set these actions that we're going to send to the model, these simulated actions. So we're going to suppose that we're going to build a simulation policy, which is the policy used for the simulated rollout. And so by calling in turn the environment model and the simulation policy, you're going to create a sequence of prediction, which I will call a rollout. Okay. For simplicity in terms of the graph, I will represent the upper graph by this slightly nicer looking lower graph. So first, before going into I2I, Imagination-Augmented agent, I will give a quick introduction to a classical model-based method, which is called Monte Carlo policy rollout. So suppose you're in an environment with a finite number of actions, say 3. I have an environment model, and I have a simulation policy, and I would like to know which of these 3 actions should I take. So one thing you can do, you can start a rollout by forcing the first action to be one of your dictionary, in this case A1, and then you use your simulation policy to make predictions. You do this for the first action, you do this for the second action, and you do this for the third action. And then, for each trajectory, you're going to effectively sum the rewards. And the behavioral policy, the actual actions you're going to send to the environment, is very simply the action that led to the maximum return, or maximum expected return if you have many rollouts. So you can see that first, this requires you to predict the rewards. Second, it requires your reward prediction to be good. If your reward prediction is very poor, you're going to take an action which actually is not optimal at all. Nevertheless, our agent is going to be inspired in some sense by this algorithm. So just to highlight what is learned and what is not learned, in this Monte Carlo policy rollout, the environment model, the red part, is learned through unsupervised learning or handcrafted. The simulation policy is learned or handcrafted, but the way you turn rollouts into actions is fixed. It's prescribed by the method. That's what we want to change. Okay, so we're going to build Imagination-Augmented block by block. So I go back to my picture of a rollout. And instead of just summing the rewards, we're going to learn to interpret, learn to extract information, squeeze the trajectory for what is valuable inside it. So we'll do this very simply by taking a neural network. In this case, we take an RNN, which is going to take the observation one by one and output some form of code. Okay, so armed with this, we're going to build things a bit more. So for notational simplicity again, this combination of the rollout and the rollout encoder, I'll denote by a simple arrow. And once again, we encode one rollout for each initial action, which is going to give you 3 codes. We send these 3 codes to a very simple neural network, which we call an aggregator, which is going to be in charge of comparing the different rollouts in some sense. And we extract an Imagination-Augmented code. So now this Imagination-Augmented code has some information about the observation, but it's pretty distant, and the model could be bad. So to make sure that this is not an issue, we also add a model-free path, which is any kind of classical model-free architecture that you may want to use. In our case, a convolutional neural network. Now you have 2 codes. One is model-free, in a sense, and the other is Imagination-Augmented. We combine them and extract a policy that we're going to take actions from and a value. And this is going to be a regular policy network, in a sense, which is going to be trained using classical policy gradient method, in our case, advantage actor critic, or A2C. One thing that I didn't mention, however, is that, if you remember, there's a simulation policy, and I didn't tell you how we're going to choose the simulation policy. So what we did is to adopt a distillation strategy. So we're in effect suppose that the simulation policy is a simple feed-forward neural network, and it's going to learn to imitate the slow, deliberate thinking of I2A into a more faster, intuitive simulation. And the hope is that we create here effectively a virtuous circle. The better the simulation policy is, the more informative the rollout will be. The more informative they are, the better I2A will get, and then through distillation, the simulation policy will get better. In that sense, you can think of I2A as a form of learned policy improvement operator, and it's related to a meta-RL. So now going back to this diagram, what are we learning? The environment model is learned by unsupervised learning. The simulation policy is learned by distillation, and the planner, in a sense, is learned by reward maximization and backpropagation. So that component, in a sense, is learned purely to maximize reward. It does not trust the model. Okay? So what did we test this on? We tested it in a classical game called Sokoban. In this game, you have the little green creature here, which is attempting to move these brown boxes onto these red targets. There's two features of the environment that I want to mention. The first is in this environment, boxes can only be pushed, not pulled. This leads to many irreversible decisions. So for instance, if Sokoban here pushes this box on the right, it gets stuck in the corner, the level will never be solved. The second is that the levels are all procedurally generated. You only get one chance per level, whether it's during training or testing. And also make sure that during testing, we solve completely new levels that we have never seen. For both of these reasons, you need to reason carefully before you act. So what do we get in terms of result? So first, this is giving you the curve for a model-free RL agent, which is a convolutional net trained with A2C. And it solves about 60% of levels after some training. It tends to be the easier one. I should mention, the levels that we generate are of average difficulty. A human will solve all of them, but for some of them, at least I need to think a bit to find a solution. Okay, so now we augment the model-free path by the imagination path and train the agent, and we find that this leads to a strongly increased performance, and it solves almost 85% of levels. The little blue line here is indicating the amount of training data roughly required to train the model. Okay, so you could say it's not entirely fair, because A2A has more parameters, so maybe standard would do better with more parameters. So we build another standard agent, which has the same number of parameters, and we find that it is indeed better, but worse than A2A, so it solves about 70% of levels. A last baseline or last check that we wanted to do is maybe I2A performs well because the network itself has a good inductive bias. Maybe this rollout encoder, which in our case was an LSTM, is very helpful in doing some form of pondering, and this has nothing to do with the model at all. So what we do is we take the exact same I2 architecture, but we replace the model by a sham model, a copy model that takes the input observation and constantly returns it. Everything else, the number of parameters is the same, it's the same amount of computation, the same training regime. And this does actually terrible. The copy model does worse than model-free and model-based. I want to quickly mention 3 additional insights. The first is that you can enroll for an arbitrary depth, and you would hope that the deeper the rollouts are, the more information they have, and the better the agent gets. And this is indeed the case. You can find that we tried from 1 to 15, and you can find that the deeper the rollouts, the better the performance of the agent gets, up to 90%, and probably higher if we went deeper. You can also find that the sample efficiency increases as well. So the more imagined experience you have, the less real experience you need. The second is environment model could be very costly, as I mentioned. It would be nice if you didn't call on the model too often. So for this experiment, we compared I2A with a strong planner, Monte Carlo tree search, and we set Monte Carlo tree search to solve the same amount of level, 87% level, 87%. And we compare the number of times that they need to call the environment model, and we find that I2A is an order of magnitude more parsimonious in its use of the environment model. Lastly, we want to see if there is some form of generalization, because after all, I mentioned forward models of environment are compositional and potentially they generalize to a different situation. And in fact, they do. And if you take an agent that was trained on 4 boxes and put it on 7 boxes, it loses performance. It solves only 50% of level, but this is far higher than the model-free method, the way it generalizes. Okay, so all these experiments are done with a model of Sokoban, which was learned purely from experience without any prior knowledge by the agent. But that model is pretty good because Sokoban is a fairly simple, visually it's a very simple environment. So what happens if you have a bad model? So we train a bad model by reducing the size of the environment model, and this is what you get. The rollouts are pretty bad. So these are 3 rollouts and the time on the x-axis. And you can find out while the first 2 predictions are pretty decent, as it goes on, it gets worse and worse, and eventually you even see Sokoban splitting in 2. So what happens if you do this? We compare 2 model-based methods. The first is I2A, and the second is the Monte Carlo policy that I mentioned earlier. And when you use a good model, Monte Carlo policy does okay. Roughly is model-free, between 50 and 60% of levels. But when you use a poor model, Monte Carlo's performance fails catastrophically. It basically starts solving almost none of the levels. However, I2A suffers from delayed learning, but it eventually gets almost to the same point. So maybe one way to think about this work is to think that this strong dichotomy between model-based and model-free methods is maybe not the right one. So maybe it is better or easier to think of it as a spectrum. On one end, you have purely model-based method like Monte Carlo search and Dyna. On the other hand, you have purely model-free, but in between you have other families. So our work is situated in what I personally call active imagination, which are agents that to compute their action, they need to make predictions. They need to make some form of prediction. So there's I2A, there is the imagination-based meta control, which is very related on learning to think by Schmidhuber, and so on. You could use the model not, so these agents require the model for training and testing. Another approach is to use the model learning to do effectively representation learning. So these agents do not require the model, the environment model for testing, but only for training. A last category that I call implicit model are models which are trained in a model-free fashion, but whose inductive bias resemble that of a model-based method. So in conclusion, we've introduced this idea of imagination, which are agents with internal environment model and that learn how to use their model. And we showed that this leads to increased efficiency and performance. They're also able to deal with imperfect models. And in future work and extension, we've started to work on abstract models in space and time, which enables us to tackle higher dimensional environments. Learn search tree, and very finally, the use of the word imagination is a bit aspirational because our rollouts look very much like simulation, like the kind of things you do in model-based RL. But this approach allows you to potentially query the model in richer ways to do non-sequential reasoning, to perhaps imagine things which are not likely, but important for you to think about maybe a worst-case scenario or so. And I'm done with the posters tonight, and there's a presentation on how to code this paper on Sunday.
Go ahead.
Hi, Dale. Could you talk a bit about how what the imagination encoder, the rollout encoder is actually looking at? So, for example, did you consider looking at nearest neighbors in the encoded space to try to see what is being captured by the learned algorithm?
Okay, so I think you asked, there's a lot of echo, sorry. I think you asked about what kind of information does the rollout encoder capture, is that it?
It's found to capture, yes.
It's hard to say. What probably is happening, so for the simplicity of the graph, I draw the RNN forward. In reality, we run it backwards to mimic something that looks like a Bellman operator. And so the hope maybe is that it learns to do something like a learn form of Bellman backup, but that learns to ignore frames which are not interesting or reward or potentially wrong. Oh, sorry. Or potentially does a slightly more higher dimensional prediction than just the reward. That's my intuition, but we want to do more work on actually figuring out what kind of information gets encoded in the rollout code. Oops, sorry.
Okay, a quick one, please.
Yesterday we heard about the rigor police. I'm here representing the hype police. I would like you to retract the word imagination or else give a cognitive psychological justification for it.
Well, I think this is we use the word imagination, and as I said, this is aspirational because we have an agent that visualizes possible futures. And
but so does model-based control in general, right? I mean, so does Monte Carlo tree search. So I know it's slightly different, but I know now those are all called imagination too. We got to leave imagination for when we're actually doing imagination, which is presumably a few years from now.
So as I mentioned in the end, the forward reasoning, which is the kind of things that you would do with Monte Carlo tree search, what we want to do and we've started doing goes beyond this kind of very sequential, ticking at the clock, t+1, t+2, and so on, method. And so, I mean, we can debate, the use of word imagination and memory, but, that's, I don't know.
Let me second Tom's.
Let's thank Theo again. Yeah. Next, we're going to have a set of 6 spotlight presentations. First one is on dual path networks.
Hi, my name is Yunpeng Chen. This is our work on dual path network together with Jianan Li, Huaxin Xiao, Xiaojie Jing, Jia Shifeng, and Shuicheng Yan. In this work, we focus on developing more effective networks that can benefit multiple computer vision tasks. We start by analyzing 2 state-of-the-art network architecture, the REST-U network shown on the left, and the densely connected network shown on the right. As you can see, the residual network adds its output back to the input, while the densely connected network concatenates its output with the input. They look very different, but in this work, we found that the residual network are essentially the densely connected network, but with shared connections. Here, we highlight those shared connections with red boxes. We found that given a residual network, one can convert it into a densely connected network. And the difference between this converted residual network and the vanilla densely connected network is that those highlight parts are shared across layers. And since the input of those highlight part is actually the same across layers, the residual network actually extracting exactly the same kind of features across the layers. So in this work, we claim that the residual network is actually more good at reusing features across layers, but may not good at extracting new features from previous layers. But for the densely connected network, since it does not have this parameter sharing mechanism, it's more good at extracting new features from previous layers, but may have some feature redundancy because crucial features might be extracted multiple times from previous layers. So we proposed our dual pass architecture, which enjoys the benefit from both the residual pass and the densely connected pass. This is an equivalent form of the dual pass network. And in our implementation, we use the bottleneck structure to build our subnetwork. And the output of this bottleneck structure is sliced into two parts. One part is to add to the residual pass. Another part is concatenated to the densely connected path. We designed 3 types of DPN with different depths, the DPN 92, DPN 98, and DPN 131. And compared with the best rest next, the DPN 98 achieved 26% less model size, 25% less flops, and consumes 8% less GPU memories. But on the ImageNet 1000 class classification dataset, it still has higher accuracy. So we slightly increased the depth from 98 to 131 and further pushed the top 5 accuracy on this ImageNet dataset. And in this year's ImageNet large-scale vision recognition challenge, we also achieved a very good result. All tasks within top 3 by using our proposed DPN as the backbone CNN. If you want to know more, please come to our poster session. It's number 130. Thank you.
Hello, everyone. So I'm going to present some work on developing a simple neural network module for relational reasoning. Relational reasoning is a core component of many of the problems that we'd like to address in machine learning. Consider the left-hand side on visual question answering. We may want to, for example, relate the attributes of certain physical objects in a scene to answer questions such as, what is the color of the cube to the left of the big metallic sphere? Or we may even want to relate non-physical entities, such as sentences, in order to answer a story, in order to answer a question about a short story. One important criteria that I'd like to emphasize about general relational reasoning is that often we want to relate entities that are not necessarily proximal in space or in time. So this means that our go-to neural network architectures, such as RNNs or convnets, might not be precisely the best architectures for general relational reasoning because they do not have the right bias, and they are biased towards considering things that are proximal in time or space. So our contribution in this direction to develop something that is perhaps a little bit more general, has a more general capacity for relational reasoning, is what we call a relational network. And it looks like this. So we start off with a set of objects, and here we denote an object by the lowercase o, so O-I, O-J here. And we feed pairs of objects from this set into a function g, which for us is just a small MLP. So importantly, this same function, the same MLP, is fed input, is the same function operating on each pair of objects from this set. So we have weight sharing across object pairs. Importantly, this means that the weight sharing is not contingent on the particular features of the object, such as where they are located spatially. We then sum all the outputs from this function g and feed that as input to another function f, which again is another small MLP. So the total output of the Rn contains information about object pairs, and it is also permutation invariant to the ordering of objects in the object set. We tested this network module on a number of different data sets. One of them is Clever. So in Clever, you have pictures like you see here, and you have shapes of different sizes, textures, colors, etc. And you are proposed a question. For example, there's a sphere with the same size as the metal cube. Is it made of the same material as the small red sphere? So these questions can get very complicated in terms of their demanding relational reasoning. So this is just a diagram of how we hooked up a relation network to a standard neural network architecture. So we start off with our image and use just a very simple 4-layer convnet to process it into a number of feature maps that are 8 by 8. And then we take each pixel vector as an object. So since we take each pixel vector here as an object, this means that objects are not necessarily tied to the physical entities that actually exist in the picture, and an object may even correspond to, say, the background. So we take all possible object pairs from using these pixel vectors, construct our object pairs, take an embedding from an LSTM that processes the question, append that to each object pair, and then push each object pair through a small MLP, 4 layers, to get our summary vectors, which we sum, and then another final MLP to get our answer at the end. So here are the results. Just to orient you, the black dashed line is the human baseline. The pink dashed line is the Q-type baseline, which is just based on the answer statistics for each question type. We have the overall score here in the top left, and we can see that we are at human performance on this particular task. And importantly, I'd like to direct you to the bottom right over here. These are the compare attribute questions, and these types of questions involve some very complicated comparisons of shapes all across the scenes. And the best baseline from the Clever paper, which consisted of ResNet embeddings with a big LSTM and stacked attention, did not perform well on these types of highly complicated relational questions, whereas our model, with just a simple convolution neural network augmented with this relation network, managed to solve these questions. I don't think I have time to go into a number of other tasks that we have done, but we also worked on a task called Sort of Clever, which more explicitly parses relational from non-relational questions. And we also worked on Babby, and we got some nice results there. So I encourage you to come see our poster if you'd like more details on that. Thank you very much.
Hi, I'm Yuhai Wu from University of Toronto. Today I'd like to introduce a new reinforcement learning method where we apply an approximate natural gradient method called K-fact to actor critic. In reinforcement learning, we'd like an algorithm that is both simple and computationally efficient. Our approach is to use natural gradient, which is a more efficient optimizer. Previously, there is a trust region policy optimization. It also uses natural gradient method, and it is very efficient in terms of number of parameter updates. However, as it uses conjugate gradient, it requires a very expensive iterative procedure for each update. So it is not scalable to modern-sized neural net. So we propose ACTOR, which stands for Actor-Critic Kronecker-factored Trust Region Method. Our main tool is to use this approximate natural gradient method called K-fact, Kronecker-factored approximate curvature. So this is a scalable algorithm. The core idea is to use Kronecker products of two small matrices to approximate Fisher matrix. Such compact representation is able to achieve a scalable commutation because it reduces large matrix operations to small matrix operations. And it can also be applied to most of the standard neural net architectures, including fully connected networks, CNNs, and RNNs. We applied this to our base algorithm A to C advantage actor critic. It is basically a distributed implementation of the actor critic algorithm with n-step return as the advantage function. So how do we apply k-fact to A2C? The procedure is pretty simple. You first need to define the Fisher matrix, and then you just apply k-fact approximation. For optimizing the actor, we follow the natural policy gradient, where we use policy distribution to construct the Fisher matrix. And for optimizing the critic, we assume a Gaussian distribution over the output and use that output distribution to construct the Fisher matrix. This is equivalent to the Gauss-Newton metric. So other details includes we rescale the updates using trust region method, very similarly to the TRPO. We also use a moving average to accumulate the Fisher statistics in order to get a best estimator for the curvature. We also asynchronously compute the major inverses to speed up in computation time. So here are some results. So the blue line is our algorithm actor. You can see in the Atari benchmark, we're able to achieve 2 to 3 times improvements in sample efficiency over the other baseline algorithm, A2C and TRPO. Similar results are obtained in the Majorco benchmark. And we also tried training continuous control policy directly from the pixel inputs, and we are able to train some non-trivial tasks in the Majorco benchmarks. So how about workout time? We have measured the workout time, and it only increases 10 to 25% of computation time compared to the A2C. So it's not a huge overhead. Another benefit of using actor is that it uses large batch size more efficiently. So the reason is that not only you can get a better estimate of the gradient with large batch size, you can also get a better estimate of the curvature using large batch size. So you can use large batch size more efficiently. We also compared our algorithm with another very popular algorithm called PPO. In PPO, it is doing mini-batch training, so it actually needs to do 320 times more number of updates for the same amount of data. However, it is still not as good as actor. In particular, in the task humanoid, showing the right-hand side or left-hand side, or right-hand side, okay. Actor is much better than PPO. And we also compared with PPO and other state-of-art reinforcement learning methods on Atari. And the curve showing blue is the actor, and it is a lot better than the other algorithms. Okay, so here are some conclusions. We also will release some other combination of k-fact and other reinforcement learning algorithms. Please stay tuned. Thank you very much. The poster is tonight. It's number 140. Thank you.
Hi, today we're going to talk to you about the transformer, why attention is a very effective solution for sequence modeling. This is work done at Google Brain. So if you want to do sequence modeling, you need to learn representations of variable length data. This is important for tasks like machine translation, summarization, and even, for example, image generation. De facto, and a very successful solution has been using recurrent neural networks that compute representations sequentially in a linear chain position at a time. Unfortunately, sequentiality limits the amount of parallelism you can do, slowing down training time. And if you want to model long-distance relationships, you have to make many hops through the network, and they can be potentially difficult to train. Many dependencies are local, and convolutional sequence-to-sequence models exploit that. They're trivially parallelizable, very fast to train. They've worked well. However, again, if you want to model long-distance relationships, you need many layers, sometimes linear or logarithmic in the input size. Attention or content-based memory addressing has been a very crucial component in standard encoder-decoder models. So we asked the question, can we use self-attention to compute representations? So if you wanted to represent the word represent here with self-attention, you take, the way we do it is we take the embedding of represent, we would compare it with the representations or embeddings at all the other positions with multiplicative interactions and gating to compute compatibilities, and then we would combine the information at all these positions weighted by the compatibility scores. Notice that this actually allows you to model both short and long distance relationships in constant time, making your model very expressive. You have the advantages of multiplicative interactions. It's trivial to parallelize, therefore really fast to train. So could it completely replace recurrence? There's been some really good previous work on using self-attention. You can, for many tasks, you can look at the paper for more details. So this is the culmination of our work, the transformer, where we essentially take an encoder-decoder architecture and we replace LSTMs with self-attention and feed-forward layers. So on the encoder side, we have stacks of self-attention layers and feed-forward layers along with positional information, because attention works on sets. We need positional information, which computes input representations. On the decoder side, we have a masked self-attention layer that sort of mimics a language model, and you can only attend to your left because we're still doing autoregressive decoding. And then this is followed by a standard encoder-decoder attention layer that attends to the the final encoder layer, and then we have a feed-forward layer, and this triple essentially repeats. This is a hyperparameter in our model. The way we implement our dot product attention is that we linearly transform embeddings into queries, keys, and values, and this amounts to the computation that this amounts to is doing 2 matrix multiplications and a softmax.
So one great thing about attention is that it is cheap. A self-attention layer is quadratic in the length of the sequence, but it's only linear in the dimensionality. Compare that to an RNN or a convolution, which is linear in the length of the sequence, but quadratic in the dimensionality. So if the dimensionality is longer than the length of the sequence, then the attention is cheaper. In practice, you can do self-attention over thousands of sequences of length, thousands of tokens, no problem. Now, one big weakness of self-attention relative to convolution is that convolutions use different linear transformations for each relative position, and that lets you know which information came from where. Self-attention is just a weighted average. So, for example, if a verb attends to its subject and to its object, then you get a mix of the two. You don't really know which is which. We solve this problem by having multiple attention layers in parallel with different linear transformations on the input and the output. That way, maybe in one of them, the verb attends to the subject, and in another one, the verbs attend to their object. This sounds expensive, but it's actually pretty cheap because we reduce the dimensionality. We got great results in machine translation, better than previous methods, and faster. We've open-sourced all of this in the Tensor-to-Tensor library, thanks to Ryan Sapasi and everyone else who's helped with that. Thank you for your attention, and come to us with any questions in the poster session. Thank you.
Hello, everyone. I'm Han Jun from Georgia Tech. This is a joint work with Elias, Yu, Bistra, and Li. We first start with one of the graph NP-complete problem, which is the minimum vertex cover. Later, we will show how to apply this general learning paradigm to other graph problems. So the minimum vertex cover asks to find the smallest vertex subset S, such that each edge has at least one S in S. It can be used to model the S optimization in social network. We first review some existing methods to tackle this NP-complete problem. The exact algorithm guarantees the optimal solution by performing search with pruning, but sometimes it's time-consuming. And the approximation algorithm has a worst-case guarantee, but empirically it performs poorly. And heuristics like picking the node with largest degree only works in some cases. But we think the main problem is they cannot learn from the same instances of the problem that was solved before. So think about a more realistic setting where the same problem is solved repeatedly with slightly different data. For example, a social network can be known as the dynamic graph with the relationships created or jobs across time, but roughly they can still be characterized using the same parametric model. So we propose to learn a better non-myopic algorithm that can generalize to unseen instances from the same distribution as in training. In our paper, we focus on the minimum vertex cover, max cut, and the traveling salesman problem. The first question is how to learn. Instead of doing supervised learning where the supervision is typically hard to obtain, we use the reinforcement learning to let the agent to improve the policy by learning from experiences. This is also inspired by the Combinatorial optimization paper. So think about the integer programming formulation of the minimum vertex cover. We can see it is natural to set the constant reward at each time step, where the reward equals to the negative of the cost. And also, the action value function takes the current partial solution and the next candidate vertex as the input, and predict the required total future number of steps to solve the problem. And if the Q function is good enough, we can simply use a greedy policy. The second challenge is how to represent your action value function. Instead of doing a feature engineering, which might be hard to construct and hard to generalize to the graphs with different sizes, we use a graph embedding model called a structure-to-vec, where the representation of the graph is learned end-to-end with the reinforcement learning framework. So the graph structure-to-vec is a message passing-like algorithm where the node representation is updated using nonlinear function of the neighborhood representation and iteratively. And in the last layer, it predicts the Q value on each node. And this is the overall learning framework. It is efficient since it can be executed in polynomial time. In our experiment, we first did some experiment on the synthetic data, where we focus on random graphs. And we compare with some approximation algorithm heuristics and also the pointer network with actor critic. And we can see in the minimum vertex cover, our performance is near optimal where the error bar is barely visible. And more results on max cut and traveling salesman problem. We also show that this achieves a better time solution trade-off. For example, for CPLX, it requires longer to achieve same solution than ours. And also, we got some good results on real-world data on MemTracker, which is from Stanford, and also the famous TSP-lib. And lastly, we want to visualize what is the strategy we have learned. And the leftmost one is ours, and the others are some known greedy heuristics. They all start from the same instances. And whenever they pick a node, we remove the node and the corresponding edges. And we can see in the 7th step, the other greedy heuristic makes the residual graph isolated, but our algorithm still keeps the connectivity of the graph. And the same thing happens for till the end of the planning. So we can see our algorithm learns a strategy which tries to keep the connectivity of the graph. This can not be simply represented by a greedy, but more requires like a dynamic programming like approach. Okay, thanks, and welcome to our poster session, which is tonight.
Hi, I'm Balaji, and I'm going to be talking about my work with my colleagues Alex and Charles at DeepMind. So we're interested in the problem of uncertainty quantification in deep learning. And let's say you're doing supervised deep learning. Let's say you're doing classification. Well, we want to not just predict the label, but also output like a confidence. And similarly, in regression, we don't want to predict a point estimate, but some sort of variance. And how do we measure uncertainty? We usually don't have ground truth uncertainty estimates itself, but there are two properties that we kind of care about in practice. And the first is what's called calibration, which is the frequentist coverage of the subjective forecast. And the second property is we would like, when the network is outputting predictions on like inputs far away from the training data, we would like it to exhibit higher uncertainty on the so-called out-of-distribution examples. And there's a lot of work on uncertainty quantification, but it's mostly around Bayesian neural nets. they work well in like small data regimes, but they are kind of hard to scale and require significant modifications to the regular training, and they don't scale very well to, say, ImageNet. So in this work, we present a simple yet surprisingly powerful non-Bayesian baseline for estimating predictive uncertainty estimates. So here's the recipe we propose. So we let a neural network output a distribution. In classification, we already do it because the softmax output is a distribution or the class labels. But in regression, in our work, we use a simple thing where the network outputs a mean and a prediction variance. And then we use a proper scoring rule as a training criterion. So log likelihood is a proper scoring rule. We could use others as well. And we also augment with adversarial training. I don't have time to go into the details, but you can think of it as a computationally efficient way to locally smooth the predictive distributions as opposed to like weight averaging, which what Bayesian neural nets do. So, and then we train an ensemble of M networks with random initialization. We tried a bunch of things, but just random initialization works quite well in practice. And at test time, you combine the predictions. So each network outputs a distribution, and then you just you treat it as a mixture of distributions. And note that we are doing model combination and not Bayesian model averaging. So to give a flavor of results, here are some classification results on MNIST. On the x-axis is the number of networks, and I'm plotting the classification error as well as the negative log likelihood and Brier score, which are measures of predictive uncertainty. The red line is just vanilla ensembles, and green line is MC dropout. And as you see that, as you increase the number of nets, not only does the classification error drop, but the uncertainty estimate also increases significantly. And all of the ensemble variants perform much better than dropout. And at the next step, the blue line combines ensembles as well as adversarial training, and we see that it improves predictive performance quite significantly on this data set. We've done a bunch of other results on SVHN, ImageNet, and regression benchmarks, and we observe similar results. And on the next experiment, we estimate predictive entropy on known and unknown inputs, which was what I mentioned in the beginning of my talk. So what we do is we train on MNIST. So we first test on the usual MNIST, and as a measure of the predictive uncertainty, we measure predictive entropy. So the lower predictive entropy means the network is very confident in its predictions. So on the known test set, of course, the network is going to be very confident. And what I'm plotting here is the histogram of the predictive entropy on the test set. So as you vary the number of networks, both on the left is the ensemble, and on right is MC dropout. You see that the network is still pretty confident. However, when you predict on this not MNIST data set, which is like images of alphabets instead of digits, which are out of distribution, the network is going to get it wrong, but at least you would like it to be less confident. So what we see is on the left, you see that a single network is actually very overconfident, even though it's completely wrong. It's very overconfident. And however, as you increase the number of nets, it's the confidence drops significantly. The predictive entropy drops significantly. However, for MC dropout, you see that there's still a spike, even as though you increase the number of samples. The number of networks in the MC dropout example, there is still like a significant chunk for which the network is overconfident and wrong. And this can be bad in practice because at least when the network is making a mistake, we're like, if it's not confident, then we can not trust the model's predictions in that setting. We have similar results on ImageNet as well, where we trained on a subset and tested on the whole other set. So that's it. If you're interested in more details, come to my poster tonight. Thank you.
That's the end of the session. Thanks, everybody.